So this lecture is on coasts and coastal processes. First, we will take a look at the edge of a continent. This is a continental margin, the edge of a continent where it meets the ocean. And there are three general sections, three major sections. We have the continental shelf, and that's a gently sloping part of the coast that's underwater. And it's pretty shallow ocean water, right? That's gradually sloping. Okay, so that's your continental shelf. And then you have the continental slope, which is a steeper area that goes down into the deeper ocean. And so does the continental rise. Okay, so these are deeper areas that bring you to the deep ocean. Now this particular diagram shows you a passive continental margin, meaning that this coast is not near any active plate boundaries. When you have a coastline near an active plate boundary, you're going to have a steep trench. For example, if you're talking about off the coast of South America, the west coast by the Andes Mountains, you have a subduction zone there. So you would have near the coastline, you have it's a steeper drop, and then you have your trench offshore. So it's not as gradually sloping down into deep ocean, it's a little bit more steep with that trench. But this particular diagram shows you a passive continental margin. So in this topic on coasts, we're going to focus on the continental shelf and the various processes that occur there. So what is a shoreline? A shoreline is the area on land that extends from where the water recedes to during low tide to the most inland area that is affected by storm waves. This is also the coast. Okay, so basically it's where the land and the sea meet. Okay, so you have your area where the water goes down the lowest during the low tide. Here's your low tide line right here. Okay. And then generally your storms are going to go all the way back here. That's where your storms are going to hit. So this is the coastal area, or the shoreline, more specifically. Okay, so more specifically, this is the shoreline. So why is it important to understand shoreline processes? We want to study tides and how it affects the shoreline. Waves. We have a process called longshore current and another process called beach drift. And these work in a similar fashion along with each other. Then we have riptide currents, which you may have heard of if you ever go to the beach, or during the summer you may hear a riptide current warning on the news. We're going to talk about beaches and shoreline erosion and deposition, sea level changes, the effects of storms such as Sandy had a large effect on our location. Much of the Earth's population lives near the shore, so it really does help to know a lot about shoreline processes if we have large numbers of people living near the coasts around the world. So the coastal zone is the most varied and rapidly changing environment and land feature on Earth. It undergoes many changes, some of which are on a large scale a large time scale and some are a small time scale. So we have global sea level changes would be a large time scale, a long time scale. Storms would be a short time scale. And then tides make the water levels fluctuate throughout the day. So that's an even shorter time scale. So we're going to start looking at shoreline processes. And the first is tides. So the water on Earth is affected by the gravitational attraction of the moon and the sun. And we have something called a tidal bulge. So here is the moon, and the moon revolves around the Earth. And we know that the Earth rotates, and those actions are important for our tides. So the water on Earth will bulge outward toward the moon due to gravity. On the opposite side of the Earth, there is going to be a bulge as well, related to equilibrium because of the spherical shape of the Earth. So you have this bulge pulling that way, and then this bulge on the opposite side of the Earth. The bulge underneath where the moon is larger than the bulge on the other side of the Earth. So then the Earth rotates, and parts of the land will rotate into the bulge and out of the bulge. Into the bulge and out of the bulge. So when a particular location on Earth goes into the bulge, that's high tide. And when it rotates and then is out of the bulge, that's low tide. And the Earth's rotation takes 24 hours, and it brings each location on the Earth's surface into that tidal bulge twice per day. So the bulge stays wherever the moon is, and then the moon also is revolving around the Earth. Okay, so wherever the moon is, that's where your bulge is, and then opposite side of the Earth. And then the Earth rotates in and out of, well, the Earth rotates while the bulge stays in the same spot. So in most parts of the world, there are 2 high tides per day and 2 low tides per day. Water levels can change a few centimeters to even 15 meters between your high and your low tides. Flood tide is what we call when you have an area that is experiencing a rise in water levels that's due to the location on Earth rotating into the tidal bulge. Okay, so that area going into the tidal bulge is leading up to having a high tide. Your ebb tide is when coastal areas are going out of the tidal bulge. So the high tide is receding towards low tide. So you have a drop in your water levels. Here is an extreme example of a large tidal range. And this is in the Bay of Fundy. So this is the same area in high tide and low tide. So this is a very extreme example, okay? Very large drop in water levels. So extreme that this boat is left on mud that's underneath the water during high tide. So the tidal ranges, or the difference between high and low tide in one day, the tidal ranges vary throughout the month due to the lunar cycle. The lunar cycle is 29.5 days. That's the amount of time it takes for the moon to go around the Earth. So tides can be more or less extreme during the month, depending on the positions of the sun, moon, and Earth, and their alignment together. So here is the Earth, then you have the moon, and then here is the sun. So when the Earth, moon, and sun are aligned in a straight line, you have all of the forces of gravity on the water on Earth are all pulling laterally or horizontally. So all of those forces from the sun and the moon, the gravitational forces, are all pulling laterally. So these moon phases are when we're going to have our most extreme tides. Okay, so that's your full moon and your new moon. Now, when the moon is in the first quarter or the last quarter, that means that there is a right angle between where the sun is pulling on the water laterally while the moon's gravity is pulling vertically. So it's a little bit more of a canceling out situation. So the sun's gravity is pulling the water that way. The moon's gravity is pulling the water that way. So it cancels it out a little bit more. So we don't have extreme tides during that period. So when the moon, the sun, and the Earth align in a straight line, it gives us our greatest tidal range of the month. And we call this the spring tide. So that's your highest high tide and your lowest low tide. And you could see the orange color is the tidal bulge related to the gravitational pull from the sun. The gray is related to the moon. And then that teal greenish color shows you the total tidal bulge from the sun and the moon. So you can see during the spring tide, everything is being pulled laterally. So it all builds up and gives you your strongest pull. So this is your greatest tidal range. Your neap tide is what we call it when we have that right angle. So here's the sun, the moon, right angle. So this shows you the moon's gravity component. This shows you the sun's gravity component. And that's going to be your smallest tidal range of the month, the lowest high tide and the highest low tide. So that gives you your lowest tidal range. The tidal range being the difference between high and low tide. Okay, so that is your neap tide. So the spring tide is the worst time of the month to get a storm, okay? If you get a hurricane or a nor'easter during a spring tide, your high tides are already the highest high tide of the month. So if you get a storm, the wind from the storm is going to push water onto the coast more. So your water levels are going to go even higher. So the spring tide is not when you want to get a hurricane or a nor'easter, if you're going to get a storm. So your tidal range can also be affected by the shape of the coastline. For example, narrow, funnel-shaped bays can give you a great tidal range. For example, the Bay of Fundy in Canada, which is right here. If you look in here, there is it's a funnel shape. Okay, it's a funnel, narrow shaped bay. So the water kind of piles up during high tide into the narrow parts of the bay. And that allows for a great tidal range. So the Bay of Fundy, which is Nova Scotia in Canada, it has the greatest tidal range in the world, and it's about 15 meters. So keep in mind, 1 meter is about 3 feet. So 15 meters is quite a large difference between low and high tide. So here are a couple of photos showing you in an area of the Bay of Fundy. So here you have the water level is out here during low tide, and here the whole area is inundated during high tide. Now we're going to talk about waves. So you have the anatomy of a wave. You have the crest is the top of the wave. The trough is the bottom of the wave. Your wave length is the distance from crest to crest. And your wave height is the distance from the bottom of the wave, the trough, to the top of the wave, the crest. Your wave period is the time that it takes for one wave cycle. So that's the passage of 2 successive crests. So if you're sitting here watching and the wave moves by, you would see between the time you see one crest to the next crest is the wave period. And the frequency is the number of wave cycles per second. So waves form from wind blowing across the water surface. And that's related to friction from wind going against the water. And the height, the length, and the period of a wave depend on the following: wind speed, the length of time that the wind has been blowing over the water, and the fetch, the distance that the wind has traveled across open water. So in other words, the greater the wind speed blowing over a longer period of time over a larger area of water is going to create larger waves. So when waves are moving in deep water, we have the wave of oscillation. So water molecules move in circular motion. And you saw that in the Bill Nye video, that the water was, the particles that were floating in the water were not moving forward. They were staying in the same area of water. So the wave is moving through the water as energy, but the water molecules are not moving forward. And again, we are talking about deep water before where the waves are breaking at the shoreline. Okay, so there is little or no movement forward. It's the wave energy that's moving forward, not the water itself. So you can think of it like an earthquake wave. When earthquake waves go through the ground, it's not moving all of the ground forward. It's a vibration going through the ground. And then I have an animation to show you. Okay, so this shows you a wave. The wave is moving across like this. And there is a seagull on the water surface. Now the seagull is experiencing the wave. The seagull goes up and then back down to its original location. So the seagull is not moving forward, only the wave is moving forward. And again, if you ever go swimming or surfing or boogie boarding, you would experience this as long as you're behind where the waves are breaking. Okay, you would feel yourself go up and then be dropped back down, and you're pretty much in the same location you were before you got picked up, right? So that's how that works. So again, wind leads to wave formation. So wave energy dissipates with depth, right? Because the wind and the effects of the wind going across the water surface are strongest at the water surface. So as you go down deeper into the water, you lose that effect from the wind. So going deeper down, the orbital motion of the wave diminishes. Below a certain depth, there is actually no more orbital wave movement. That depth is called wave base. Wave base is approximately half of a wavelength. Okay, so you take the wavelength, you cut that in half, and that distance approximately is your wave base. Okay, so below that wave base, water molecules are not affected by the waves. So up until now, we've only been talking about deep ocean water behind where the waves break. Now we're going to look at what happens to waves as you approach the shallow water at the coast. Okay, so here's deep water, deep water. Now this wave is starting to approach the shallow water. And now the depth of the water here is now the same depth as down to wave base. So now the wave movement is interrupted by touching the seafloor. So now at this point, you would start to see a little bit of movement at the surface of the water. That's where if you ever go swimming in the ocean, you start to see a little bit of like this white line forming, and you start to see a wave start to rise up a little bit, okay? So the orbital, these circles, right? As soon as it starts touching the bottom, as soon as the lowest orbital movement is touching the bottom of the seafloor, the bottom of this wave slows down while the top of the wave is still moving forward at the original speed. So what happens is the wave starts toppling over. It's similar to if I were to walk across a room and if I trip on the floor. Like if just, like, let's say my shoe kind of just gets stuck on something and I trip, my head would move forward because the top of my body didn't get stuck on the floor, only my feet did. So my feet would slow down while the rest of my body is still moving forward. So I would topple over. The same thing's happening with the wave, okay? The wave is toppling over because like the top of the wave is still moving. Okay, so here it's continuing to topple over, and that's where you see a more significant wave with like the white part of the wave that you would look for if you boogie board or surf, or if you like to swim and like dive into the waves. That's what you're looking for. And then as that wave goes into more and more shallow water, the wave is going to form a breaker, which is steep. It's like a steep wall of water. And then that topples over and crashes. So this whole process is called wave shoaling. So when a wave enters shallow water, the wavelength shortens. Okay, so here the crest to crest, crest to crest. The wavelength is starting to get shorter. The height of the wave is getting higher. And then eventually that wave topples over and breaks. Okay, so this process is wave shoaling. And I have this animation to show you. Okay, so this animation is showing you waves in deep water, and then they approach shallow water at the coast. The wave length is getting shorter, and the wave height gets longer. Okay, and then we get our breaker. That's when the wave height increases until the wave is too steep, and then the crest plunges forward. So then we're going to talk about wave-generated currents, specifically rip currents. So here is a sign that talks about warnings for rip currents. It says, if caught in a rip current, don't fight the current, swim out of the current and then to shore. If you can't escape, float or tread water. If you need help, call or wave for assistance. Okay, and then it shows the rip current is this narrow current that's going from the coast out to sea. Okay, it's a very narrow current, but it rushes quickly and strongly out to sea. So it's showing you to swim out of the current. Okay, so instead of trying to swim back to the shore, like against the current, you're supposed to swim sideways to get out of the current. So what is a rip current? When water is brought on shore, when waves break, the water piles up and builds up on the beach. So then it backwashes out to sea. And that backwashed water finds a topographic low. For example, between sandbars that might be underwater near the coast. So then the water is going to flow quickly back out to sea in a narrow current between sandbars or any topographic low that might be in the sand under the water. So it's a fast surface current that's rushing back out to sea, but it's narrow. It could travel hundreds of meters away from the shore, and it's very strong, so it can carry people out to sea. Even lifeguards who are strong swimmers, it could carry them out. So again, if you ever get stuck in a rip current, you're supposed to swim not back to shore, you're supposed to swim out of the current, parallel to the shoreline. So when you look at the water here, you can see some of the areas look kind of smooth, right? So rip currents typically extend from the shoreline through the surf zone and past the line of breaking waves. And for example, right over here, the water looks kind of smooth. That's what they mean. Okay, over here, you see this line is pretty smooth, right there. Okay, like you have this white line with waves, and then over here as well. But right here, you don't. And then you have this foamy area where it's white. That tells you that's a rip current, okay, where you have the water going back out to sea. Okay, so these are all rip currents. And here is from Google Maps, you can actually see rip currents on the image. So over the summer, you just look for a beach on Google Earth or Google Maps. You turn on like the aerial view and you can see rip currents. Then we have near shore environments. So near shore is the area from where waves begin to shoal up to the low tide line. Okay, so here is your shoaling zone. Okay, so that's again, that's where your waves are getting interrupted by the seafloor, and the base of these waves start to slow down while the top is still moving forward, right? This is your shoaling area. And your low tide zone is right here. Okay, so it's not at the shore, it's near the shore. And then I have a little video clip to show you. So you just watched that little clip from the movie Beach River of Sand that talks about longshore current. So we're going to go into the details about that. So first, why do waves hit the coast at an angle? Generally, it's because you have waves that are generated by storms that form offshore, and those waves that form offshore radiate outward in all directions, and they eventually hit the coast. So these waves are going to hit the coast at an angle, these hit at an angle. Usually waves are not hitting the coast straight on. Okay, it would only hit straight on, like right there. Okay, anywhere else, it's going to be at an angle. So the waves actually do straighten out a little bit though. And that's because as the wave, like this whole line here is part of one wave. So when this part of the wave hits the shoreline, this part of the wave is slowing down. But this part of the wave is still moving in deeper water. So it's still able to move at the original speed. So that's going to keep moving. This is going to slow down. So that causes the wave to move on an angle a little bit and kind of straighten out a little bit straighter. So when it hits the coast, it's a little bit straighter than this angle. You see how like this is more angled. This is a little bit straighter, parallel to the coast. It doesn't become completely parallel to the coast though, but is a little bit straighter than it was before. So then after these waves hit the coast at that angle, it causes water to build up in the surf zone. Okay, surf zone is over here. That's where the breakers are hitting the coast. So all this water is hitting the coast and it builds up and you get this current. In this case, because the angle is that direction, the current is going to form that direction. So that's your longshore current. And it travels in the nearshore zone around the surf zone, and it is parallel to the coast. And the longshore current forms because waves hit the coast at an angle, causing water to build up and move along the shore. So here you have your water waves moving at this angle like this direction. The water builds up along the coast and forms this longshore current. And then you have this enlarged part of the diagram that shows you your longshore drifts, or your longshore current is going this direction. And then you have this piece over here, like a little pebble. It gets pushed onto the beach, but because you have this angle, it gets pushed that direction. And then the backwash of the wave goes perpendicular from the beach into the ocean. So when the materials that are carried in the wave are put on the beach, they go at an angle. And then when the water rushes back out to the sea, the backwash, that's perpendicular to the ocean. So you end up with this zigzag pattern of how materials move along the coast. That is called beach drift. In this diagram, they call it longshore drift, but that's your beach drift. Just add that here to be consistent with the notes. Okay, so specifically, this is your beach drift. And materials move down the shoreline because of that, as well as the longshore current. Now, if you've ever gone swimming in the ocean, you've probably experienced this type of movement. Okay, so here I have the term beach drift, by the way. Okay, so net movement of sand along the coast, sediments move along the beach in a zigzag pattern. That's in your swash zone. And that's as the waves move on and off shore. Now, the term longshore transport, which you'll see in some other slides, that is the net movement of sediments, usually sand, moved by beach drift and longshore current combined. Okay, so that's your longshore transport. You have your beach blanket here. Okay. That's, let's say this is me. Okay, so I come to the beach. Here's my beach blanket. Okay, hey, let's go swimming. Okay, so I go in the water. I'm swimming, playing in the water, boogie boarding, whatever. Okay, I'm in the water for like an hour. I don't realize it, but I am being moved along the beach with these movements here, the beach drift and the longshore current. Okay, I don't realize it yet, but now I want lunch, I'm hungry. Okay, so, oh, I'm gonna go out of the water, right? I go onto the beach. Hey, where's my blanket? Where's my stuff? And then I look around and I see, oh, it's all the way over here. How did that happen? Okay, so then I go back. So what happened was I got caught up in that movement, the longshore transport and the beach drift, that whole movement, right? The longshore transport. You end up getting caught up in that movement, just like the sediments in the water. So then we have depositional features related to nearshore currents, specifically that longshore transport. So we have features called spits. These are finger-like projections that extend out into a body of water. They are composed of loose sediment and are formed by longshore transport. Okay, so in this case, you have longshore transport that would occur along the coast here, moving, moving, moving. And then here's the end of the coast, but the longshore transport kept moving. So it accumulated sediments extending outward into this water. And it built up this projecting out finger-like projection here. That's your spit, okay? And it grew and it grew and it keeps growing. And you keep building up sediment with that current, with that longshore transport. A bay mouth bar is a spit that closes the mouth of a bay. So this is a bay mouth bar that closes off this bay near Bridgehampton. This is the south shore of Long Island. So here's a bay and it's cut off by this bay mouth bar. Here's another bay mouth bar. It's called the Curonian Spit, but it's a bay mouth bar pretty much. There is this tiny little inlet here. I don't know, they may actually dredge this to keep it open so that you could pass in there. I'm not sure about the details about that. But generally, this is a bay mouth bar. It cuts off this lagoon from the Baltic Sea, where this spit grew that direction. It kept growing until it cut off the lagoon from the sea. Then we have barrier islands. These are long, narrow islands parallel to the shore. They are separated from the mainland by a lagoon or a marsh or a bay. Okay, so here in this photo, you have bay water, right? It's gonna be marshy, usually it's marshy. And then here is your beach along the barrier island. This is an example from the Outer Banks in North Carolina. Barrier islands form at gently sloping continental shelves, which, as I mentioned at the very beginning of the lecture, that is going to be related to passive continental margins. Typically, we find barrier islands along the Atlantic coasts and the Gulf coasts of the US. I mean, they're found around the world as well, but for the US, that's generally where we find them. This is a typical profile of a barrier island. So you have your beach face, then you would usually have dunes, then you either have trees or shrubs, then you have a salt marsh, and then a bay or lagoon on the other side. So that's the beach, and then in between over here you would have some sand dunes, and then usually you have some sort of vegetation. Back here you have some vegetation. And then you would have salt marshes. This doesn't follow exactly the profile I just showed you, but it is close. And then your marshes are on the back. Here are barrier islands along the New Jersey shore. Now you have a point where the longshore transport changes direction. So at some point, the transport moves southward, and then over here it moves northward, and then all the way here by the Raritan Bay and Sandy Hook Bay, you have a spit. That's the Sandy Hook Spit. So it grows northward with longshore transport. And here are some barrier islands along the south shore of Long Island. So barrier islands. Okay, these are this is a baymouth bar. I showed you a map of this area before, the baymouth bar. Okay, and the south part of these barrier islands, that's all beaches. For example, Jones Beach, Long Beach, and then you have the bay side, right? So here's a closer look, right? So you have beach, and then behind that you have these bays where it's lots of salt marsh areas. This is Jamaica Bay over here, which is a large bay. Okay, and that's your longshore transport direction. And then this whole area here is the Rockaways, and that movement would be that direction. And here is the Sandy Hook Spit growing that direction. So because of the movement of sediment, the harbor over here gets dredged every once in a while, where they remove sediment from the seafloor so that you can still have large boats go in there. So there is quite a bit of engineering and dredging and things like that that occur in the area because it is busy with commerce. So, you engineer and fix and maintain the different parts of the waterways, the local waterways. So that brings us to the end of part 1 of the coast lecture.